In this video, I'm going to work through every question on the Cambridge exam from 2020, May, June, Pure Math 3, and this is the exam number 33 from that series. We're going to work through the questions to show you that it's possible to do the whole exam in the time given, probably even less than the time given, just by spending a bit of time thinking about the question and working out the best way to approach the question. The start of every question is tagged, so you can just jump to whichever question you need help with or are interested in. All right, let's get to it. Solve the inequality. The absolute value of 2x minus 1 is greater than 3 times the absolute value of x plus 2. When we have modulus signs or absolute value signs on both sides of an inequality, the easiest way to make progress is to square both sides. Because if you square a negative, you get a positive. You square a positive, you get a positive. So it doesn't matter too much whether x is negative or positive. So that's what we're going to do. 2x minus 1 squared is going to be greater than 3x plus 2, and put double brackets there and square it, because that squared gets distributed. Okay, the next line, we expand the brackets. 4x squared minus 4x plus 1, it will be greater than 9, because that's 3 squared. Open brackets, x squared plus 4x plus 4, which is x plus 2 squared. All right, we can distribute the 9. 4x squared minus 4x plus 1 is greater than 9x squared plus 36x plus 36. All right, collect like terms. Because 9x squared is larger than 4x squared, I'm going to move everything from the left side to the right side, and that will just leave us with a 0 on the left side. So 0 is now greater than 9 minus 4 is 5x squared plus 36 plus 4 is 40x squared, 40x, not squared, and 36 minus 1 is 35. All right, 5 is a factor of every coefficient there, so we can divide everything by 5. Okay, let's change sides. Remember, if we just flip the side, the sign has to turn around as well. So we'll have x squared plus 8x plus 7 is less than 0. So let's say a quadratic equation is less than 0. When is a quadratic equation less than 0? When it's below the x-axis. So we factorize it and we'll get what multiplies to 7, adds to 8, 1 and 7. So it's x plus 1 times x plus 7 is less than 0, which tells us we should actually draw a little graph so that we understand what's happening here. The quadratic's going to be a smiley because in front of x squared is positive, and we know the roots are going to be -1 and -7 because that's what makes the brackets 0. So if we draw the quadratic and have a look at it and say, well, where is the quadratic less than 0? And that's of course saying where is the y value of the quadratic less than 0? And that's below the x-axis. So we say, well, what are the x values when this quadratic is below the x-axis? Well, x is going to be less than -1, and x has to be greater than -7. So we can just write that very simply. -7, x is greater than and less than -1. And that's a good answer. Question 2, we have to find the exact value of a definite integral from 0 to 1 of, in brackets, 2 minus x e to the -2x dx. Well, it's going to be a lot easier for us if we expand those brackets first. So let's do the integral 0 to 1, 2e to the -2x minus x e to the -2x dx. Okay, so the first term there, that's easy to integrate. The second one is there's an x and there's an e to x, so there's 2 x variables, which, as it stands, integration by parts is what we have to do to try and get rid of the x. The integration by parts formula is just a rearrangement of the differentiation product rule. And so we have the integral of u derivative of v equals uv minus the integral of derivative of u times v, where u and v are functions of x. So u is, in this case, we're going to say x. Why? Because the derivative, u dash, is going to be 1. And that would make v dash equal to negative e to the -2x. Right? I took the negative sign and I put it with the e because you can see that when you're going to integrate that, a negative is going to come from the exponent there. And if we have a negative out the front, they're going to cancel out. So that would be nice for us to associate the minus sign with the e to the minus 2x instead of with the x, right? So v is the integral of negative e to the negative 2x, and that means the minus 2 is got to be cancelled from out the front. So we're going to multiply the negative 1 by negative a half, leaving us with a half e to the minus 2x. All right, they're all the parts, and we can put this together. So let's just look at the integration by parts section. The integral of negative x e to the minus 2x dx is equal to the u, which is x, times the v, which is a half e to the minus 2x, minus the integral of u dash, which is 1, times v, which is a half e to the minus 2x dx. And rearranging the first term, we get a half x e to the minus 2x, and doing the integration. The minus 2, once again, is going to have to be cancelled, and so we're going to multiply by negative a half, which turns it into plus, and a half times a half is a quarter, e to the minus 2x. And this being an indefinite integral, we would put a plus c on the end there. Okay, let's actually go back to our definite integral now and put it all together. So the integral from 0 to 1 of 2e to the minus 2x minus x e to the minus 2x dx is going to equal to the first term that we hadn't talked about there. The minus 2 is going to come out the front. We're going to multiply by negative a half, and that cancels the 2, turns it into negative 1. So we have negative e to the negative 2x plus a half, what we wrote before, x e to the negative 2x plus a quarter e to the negative 2x, and it goes from 0 to 1. It probably would be good to simplify before we substitute. So let's put the e to the minus 2x terms together. We'll leave the x out on its own. That leaves us with a half x e to the minus 2x, and minus 1 plus a quarter is minus 3/4 e to the negative 2x. All right, substituting 1 in for x, we'll get a half, x is just 1, e to the minus 2, minus 3/4 e to the negative 2 again. And then we subtract, we put 0 in, and the first term is just going to be 0 because of the x. And the second one, we put 0 in. When the exponent is 0, the power becomes 1, and so we're just left with minus 3/4. Moving on, then we can combine the first two terms. A half is 2/4, so we have 2/4 minus 3/4 is negative a quarter e to the negative 2 plus the minus turns into a plus 3/4, and that's a good enough answer. You can make it look slightly better maybe if you put the positive term out the front with 3/4 and then minus a quarter e to the minus 2, or you can have a 1 over 4 e to the positive 2. Question 3 says, show that the equation ln in brackets 1 plus e to the minus x, close brackets, plus 2x equals 0 can be expressed as a quadratic equation in e to the x. That just means where you would normally have an x in a quadratic as the variable, you're going to now have e to the x as the variable. So first thing we should do is get rid of the ln. So let's take the 2x to the other side. We'll get ln 1 plus e to the minus x is equal to negative 2x. Then we can unwrap the log, of course. The 1 plus e to the x is now going to equal the e, which is the base from the ln, to the minus 2x, which is the exponent. Okay, that kind of looks like a quadratic because it has like e to the negative x and e to the negative 2x, but the issue you have there are the negative signs, and we need to somehow turn those to positive signs. And the way we can do that is multiply both sides of the equation by e to the positive 2x. On the left side, the e to the 2x is going to multiply by 1 and make e to the 2x. E to the 2x times e to the negative x will make e to the x, and of course on the other side, e to the minus 2x means it's on the denominator. And you have the same thing on the numerator, and denominator just turns into 1, or you can use an exponent law and get e to the minus 2x plus 2x on the exponent, which makes e to the 0, which is 1 as well. All right, that's the quadratic. We can make it look exactly like a quadratic if you want. We just say e to the x in brackets squared plus e to the x minus 1 is equal to 0. Part B says, hence solve the equation and what we were given initially. Solve that, giving your answer correct to 3 decimal places. All right, so we're not going to use what they gave us. We're going to use the quadratic that we've transformed it into because we know how to solve a quadratic. We either factorize it, use the quadratic formula, or complete the square. In this case, it's hard to factorize. We can't find, well, we wouldn't be able to find two numbers that multiply to -1 and add to 1. And so we'll just go to the quadratic formula. Hopefully you remember, that is x is negative b plus or minus square root of b squared minus 4ac all divided by 2a. But the variable is not x. In this case, the variable is e to the x. So e to the x is equal to -1 plus or minus the square root of 1 squared, which is 1, minus 4ac, 4 times 1 times -1, all divided by 2 times 1. All right, that simplifies to -1 plus or minus root 5 divided by 2. We need to be a little careful with this, and because some answers are not possible. So we need to think about what is happening and see if all the answers are possible. It's always a good thing to be thinking. All right, so in this case, we have a quadratic equation, e to the x, which equals something. Now we should consider what the graph of e to the x looks like. So if we put a y-axis and an x-axis and we draw the graph of y equals e to the x, we see that it is always above the x-axis, which means e to the x can never be negative. So let's consider the answers we got. E to the x is -1 plus or minus root 5. Now, if you take -1, you notice that it's negative. And then if you subtract another value, like root 5 is just a number, it's going to get more negative, and therefore we're going to have a negative answer. Well, that's not possible because e to the x cannot be 0 or less. So the only answer would have to be e to the x is -1 plus root 5 on 2. Is that going to be positive? Well, yes, because 1 squared is 1, 2 squared is 4, and so root 5 is slightly more than 2. So if we put it into our calculator, we will get e to the x is equal to approximately, evaluating the fraction above, 0.618. That's rounded to 3 decimal places. Always use the exact value in further calculations. We can find x, therefore, is equal to, turn it into a log, ln, which is log base e of 0.618. Put in a calculator, we have our answer. X is approximately -0.481. Question 4. The equation of a curve is y equals x inverse tan of a half of x. We have to find, part A, dy dx. All right, so as soon as we see that, we see x is a function. The inverse tan of x on 2 is a function. So we have a function times a function. We need to do the derivative. We're using the product rule. And the product rule is my two equations, uv is equal to the derivative of u times v plus u times the derivative of v. Okay, and in this case, of course, u is x and v is the inverse tan of x on 2. So that means dy dx is equal to derivative of x is 1, and we just leave the other part the same, inverse tan of x on 2. We're going to add, this time we leave x the same, which is the u, and we're going to do the derivative of the inverse tan x on 2. All right, your formula sheet is extremely helpful in doing derivatives and in integration. So always look at it whenever you have a calculus question and see what help there is. As it turns out, there is a formula for the derivative of the inverse tan of x, and that becomes 1 over 1 plus x squared. But we don't have that. We don't have just an x in the inverse tan, which of course means we need to use the chain rule. So we're going to do, what's the function inside of tan? X on 2. What's the derivative of that? the derivative of that is a half. So we put a half out the front, and then we do what the derivative of the function is, with the variable being x on 2. So we'll have 1 over 1 plus, in brackets, x on 2 squared. Okay, we can make this look a little better. The inverse tan of x on 2 plus x over 2, open brackets, 1 plus x on 2, sorry, x squared on 4. We can square the x, can square the 4, square the 2 to make 4. Okay, we can still make it look better. If we multiply the top and the bottom of the fraction by 2, because there's a 2 out the front, it will get distributed in and it will get rid of the fraction inside the bracket. So that will definitely look better. And we will get dy dx is equal to the inverse tan x on 2 plus 2x over 4 plus x squared. And I think that's as nice as we can make it. And for part B, we have asked the tangent to the curve at the point where x equals 2 meets the y-axis at the point with coordinates 0p, find p. Okay, so they're asking us to find the equation of a tangent, so we're going to use the derivative and a point, which we'll find the equation of the straight line, which is the tangent, and find where it meets the y-axis. And the y value is p, and that would solve it for us. So let's take x equals 2. We just found the derivative, so if we put that into the derivative, we will find the gradient of this straight line. That gives us dy dx is the inverse tan of 2 on 2 plus 2 times 2 divided by 4 plus 2 squared, which simplifies to inverse tan of 1 is 45 degrees, but remember we're doing integration, differentiation. You have to work in radians for these formulas, and so we need an angle in radians, which is 45 degrees, and that is pi on 4. Plus, the fraction simplifies to just 4 over 8, which is a half. We can find out the value of y by putting 2 into the original equation, and we'll get y is equal to 2 times the inverse tan of 2 on 2, which again is just the inverse tan of 1, which is pi on 4 times 2. That becomes pi on 2. All right, so now we have a point, which is x is 2, y is pi on 2. We have the gradient, which we can write as pi plus 2 over 4. And we are trying to find where it crosses the axis. So we want to find the equation. The equation of a straight line, of course, is y equals mx plus c. Let's put in the x, y, and m, and we'll get pi on 2 is equal to pi plus 2 all over 4 times 2 plus c. Rearranging gives us c is equal to pi on 2 minus pi plus 2 over 2, and we can turn that into a single fraction where c is equal to pi minus pi. The minus sign gets distributed to the 2 as well and becomes minus 2 over 2. And that just means that c is equal to negative 2 on 2. And that's our p. So therefore, the value of p is minus 1. We could write a sentence if we want. The y-axis intercept is 0, minus 1. Question 5, by first expressing the equation, tan theta, tan in brackets theta plus 45 degrees, is equal to 2 cot 2 theta as a quadratic equation in tan theta, solve the equation for theta is between 0 and 90 degrees. Okay, there's a few things that are going to help us, but the question tells us to express everything in tan theta. So we need to turn the tan theta plus 45 to just tan theta. We need to turn the cot 2 theta, which of course is 1 over tan of 2 theta, into just tan thetas. We need to get rid of the 2 as well. So on our formula sheet, there's a few things that would help us here. The first one would be tan of a plus b is tan a plus tan b over 1 minus tan a tan b. The next one that would help us is tan of 2a is equal to 2 tan a over 1 minus tan squared a. And we're going to produce tan 45s. So one thing we should remember is the tan of 45 is just 1. And replace it as soon as you can. because that will be helpful. Right, well, let's step through this kind of slowly. The first thing we'll do is we'll take the tan theta plus 45 and expand it. And so we'll end up with tan theta multiplied by tan theta plus 1 over 1 minus tan theta is equal to 2 over tan of 2 theta. So we've turned the cot 2 theta into 1 over tan of 2 theta. All right, when we did the expansion of theta plus 45, we got tan theta plus tan 45. We turned that tan 45 straight away to 1. And on the bottom, we had 1 minus tan theta times tan 45. We turned that tan 45 to 1 as well. And 1 times tan theta is just tan theta. And so tan 45 is now gone from our equation. Because all the tans are on the left side, I'm going to bring the tan 2 theta up to the other side, and let's move the tan single theta up on top of the fraction. And we'll get tan of 2 theta multiplied by tan theta in brackets, tan theta plus 1 divided by 1 minus tan theta is equal to 2. I'm not going to expand those brackets because it's nice to have things in a factorized form like this. Hopefully something will cancel at some point. Okay, we can now take the tan of 2 theta and expand it, so we just have tan thetas. Tan of 2 theta will become 2 tan theta divided by 1 minus tan squared theta, and we're multiplying it by tan theta in brackets, tan theta plus 1 divided by 1 minus tan theta, which equals 2. We may notice that we have 1 minus tan squared theta, which is the difference of perfect squares, because we could consider that to be 1 squared minus tan squared. And when you have a squared minus b squared, you can turn that into a plus b in brackets times a minus b in brackets. And that looks like it will be very helpful. So let's do that and multiply those two fractions together. We'll get 2 tan squared theta, because we have tan theta times tan theta, multiplied by, in brackets, tan theta plus 1, all divided by 1 plus tan theta, 1 minus tan theta, and 1 minus tan theta, and that equals 2. All right, that was helpful because we can cancel tan theta plus 1 from the numerator and denominator, and we haven't really eliminated any variable. Like usually you have to be concerned about if you cancel a variable out or if you just eliminate a variable, you can run into problems. But in this particular case, the numerator and the denominator are both the exact same value. And so they'll turn into 1. If we did the division, we would have 1 times the rest. And so the rest of the fraction still just has to equal 2. And those two variables are doing nothing. Like the theta could be anything in there. So let's bring the bottom of the fraction up to the other side now. And we will have 2 tan squared theta is equal to 2, open brackets, 1 minus tan theta squared. Right, well, the 2's can just cancel. Divide both sides by 2, and let's expand the brackets. And we'll get tan squared theta is equal to 1 minus, and we're going to do 2ab, so it's 2 times 1 times minus tan, which is minus 2 tan theta, plus the second term squared, 10 times tan, well, negative 10 times negative 10 is positive tan squared theta. And that looks like a quadratic, except the tan squared theta can be subtracted from both sides. And it's not a quadratic. All right, but we can do that. So let's subtract tan squared theta from both sides. And rearrange, let's take the minus tan theta over to the left side. We'll get 2 tan theta is equal to 1. So tan of theta is equal to 1/2. And if we put that into a calculator, we'll get theta is equal to 26.6 degrees. And because our answer has to be between 0 and 90, that's the only answer we can have. Just mildly concerned that we didn't actually solve a quadratic. But we didn't do anything wrong, so I think we're all good. Question 6. A. By sketching a suitable pair of graphs, show that the equation x to the 5 equals 2 plus x has exactly one real root. Okay, so to sketch it and show, we would sketch the graph of x to the 5, and we would sketch another graph for 2 plus x and show that they only intersected one place. So simply draw some axes, y-axis, x-axis, and what does x to the 5 look like? Well, when x is positive, it's going to escalate pretty quickly. As x gets higher and higher, y is going to get larger very quickly. And when x is negative, you raise it to an odd power, you're going to get a negative answer. So it's going to be symmetrical in some manner, but going negative very largely. Okay, it will go through 1, 1. When x is 1, y is going to be 1. It goes through 0, 0, and it will go through negative 1, negative 1. For the other equation, y equals 2 plus x. It's a straight line, gradient of 1 and a y-intercept of 2. So let's mark 2, draw a line with a gradient of 1, and it should only cross our other graph once. Okay, we should say something about this to finish it off. As there's one point of intersection, the equation x to the 5 equals 2 plus x has only one real root. Part B, show that if a sequence of values given by an iterative formula, x to the n plus 1 is 4 times x to the n to the power 5 plus 2 divided by 5 times x to the n to the power 4 minus 1, if that converges, then it converges to the root in the equation in part A. Okay, so often we've tried to take the equation and make an iterative formula. This time they've given us the iterative formula and said show that it actually matches the equation. So all we have to do is work backwards on this. And what we do is for it to converge, x to the n plus 1 is going to equal x to the n on the convergence. So we're just going to make all the x n's simply x and then rearrange it, and we will get, well, let's take the denominator up to the left-hand side and get x times, in brackets, 5x to the power 4 minus 1 is equal to 4 times x to the 5 plus 2. Expand the brackets. 5x to the 5 minus x equals 4x to the 5 plus 2. Group like terms, the 4x comes over and the x goes over to the right side. We'll get 5x5 minus 4x to the 5 is equal to 2 plus x, which gives us what we were looking for. X to the 5 is equal to 2 plus x. So if it does converge, it will meet the criteria of the initial equation. And part C says use the iterative formula with initial values of x1 is 1.5 to calculate the root, correct to 3 decimal places, give the result of each iteration to 5 decimal places. Okay, so even if you couldn't do part B, you should do this part and try and get a few marks. Just so we can see the formula that we're using, we're taking it straight from part B. X n plus 1 is equal to 4 times xn to the power of 5 plus 2 divided by 5 xn to the power of 4 minus 1. Right, so initially we write x1 is equal to 1.5. Now we set up our calculator so that we can just keep pressing the execute or the equals button and get each consecutive number. So in your calculator, you should put 1.5 and then answer or equals or execute, whatever your button is. And then on the next line, we're going to use the answer, the previous answer, wherever we have an x. And that's going to help us just continue to press execute and get the numbers. So the numbers turn into x to the 2 is 1.33162 was rounded up. X to the 3 is equal to 1.27352. x4 is equal to 1.26724. x5 rounds to 1.26717. x6 rounds to the same, 1.26717. All right, we can stop here. We're very confident that 3 decimal places is going to be accurate solution. So the solution x is approximately equal to 1.267. Question 7 says, let fx equal 2 over, in brackets, 2x minus 1 times, in brackets, 2x plus 1, express the function of x in partial fractions. All right, well, the good news is the denominator is already factorized, and this is the simpler version of finding the values that we need. And so we can simply write 2 over 2x minus 1 times 2x plus 1, and we break it up into a over 2x minus 1 plus b over 2x plus 1. And they're our partial fractions. Done, right? No, of course, we have to find out what a and b are. So how do we do that? Well, because they equal each other, to get back to the left-hand side, we would cross multiply, and the denominator would become 2x minus 1, 2x plus 1. The numerator becomes a times 2x plus 1 plus b times 2x minus 1. And that's going to equal the numerator of the left-hand side, which is 2. Okay, so now we have this equation, and it's true for all values of x, which means we can just put any particular x in that we want and see what happens. So we choose wisely, and we say, look, if x was a half, then what's coming after the b? You get a half of 2, which is 1. 1 minus 1 is 0. 0 times b is nothing. It's not there. And so if we make x a half, we only have the a variable, and we can work out what it equals. Right, so we get 2 times a half is 1, plus 1 is 2, and we'll get 2a is equal to 2, which of course means a is going to equal 1. And then we choose again, how can we eliminate the a, or can we eliminate the a? And yes, if we make x negative a half, we would get negative a half times 2 is negative 1, plus 1 is 0, times a, and a is gone. All right, so if we go to the b side of things, we get 2 times negative a half is negative 1, minus another 1 is negative 2. So we would have negative 2b is equal to 2, which means b is equal to negative 1. And we can just put it all back together to express fx in partial fractions as 1 over 2x minus 1 plus negative 1 over 2x plus 1. Or you could have a minus sign between those fractions. Part B, using your answer to part A, show that the function of x squared is equal to this large thing. Okay, so we'll take our answer and we'll square it. So we have the function of x squared is equal to, in brackets, 1 over 2x minus 1 over 2x plus 1, all squared. And so that's a plus b squared, a squared plus 2ab plus b squared. So let's do that. We're going to square the first term, and 1 squared is just 1. So we'll have 1 over 2x minus 1 squared, and then there's a minus sign there, so it's going to be minus 2 times the first one, which is 1 over 2x minus 1, times the second one, 1 over 2x plus 1, plus the second term in the bracket squared, and so negative times a negative makes a positive, so it'll be 1 over 2x plus 1, which the denominator is squared. Of course, when you square 1, you get 1 on the numerator. Okay, the middle term we can kind of put together. Maybe it will be enlightening if we do. And we'll get 1 over 2x minus 1 squared minus 2 over 2x minus 1, 2x plus 1, plus 1 over 2x plus 1 squared. Well, that middle part, if we pay any attention, that's the function of x. So we can replace it with the function of x. But in this case, there's a minus sign out the front, and so that minus sign is going to get distributed into the function and change the signs of every term. So for the final line is what we have to show is 1 over 2x minus 1 squared minus 1 over 2x minus 1 plus 1 over 2x plus 1 plus 1 over, in brackets, 2x plus 1 squared. Part C, hence show that the definite integral from 1 to 2 of the function squared is equal to 2 on 5 plus a half ln 5 on 9. Okay, well, the good news is even if you couldn't do part B, you can use what they give you in part B to do part C. And so we're just going to swap out the function squared and replace it with all the terms that they gave us. And so the integral from 1 to 2 of function squared dx is equal to the integral from 1 to 2 of, let's put everything on the numerator, 2x minus 1 to the negative 2 minus 2x minus 1 to the negative 1 plus 2x plus 1 to the negative 1 plus 2x plus 1 to the negative 2. Okay, we integrate each part. We're going to get, for the first one, the 2x minus 1, we're using the chain rule, and so the negative 2 goes back to negative 1, and the minus 1 would have come out the front, so we need a negative to replace it, and the 2x minus 1 would have put a 2 out the front when you differentiate it, so we need a half to remove it. And so we're going to have negative a half of 2x minus 1 to the minus 1. And for 2x minus 1 to the negative 1, that's a log function, so we'll have ln 2x minus 1. And then the 2x minus 1 would have been differentiated and put a 2 out the front, so we need to get rid of the 2 by multiplying by a half. And we're good there. For the next one, again, it's another log function, or ln, 2x plus 1 this time. And again, the 2x would put, when you differentiate, would put a 2 out the front, so we need a half to get rid of that 2. And for the final part, we have a chain rule again to the power of negative 2, and so the brackets stay the same. The power goes back to negative 1. The negative 1 would have come out the front, so we need negative to get rid of it, and the 2x would put a 2 out the front, so we have to put a half there to remove that. Okay, we can make this look a little nicer by doing a couple of things. You might notice every term has got a half, and most of them have a negative a half. So we can take a negative a half out. Let's factorize it out. Because it doesn't have a variable, it doesn't need to be in the definite integral brackets. It can just pop out the front of those brackets, and that will make our life a lot easier. So inside the brackets, we're left with the 2x minus 1 to the negative 1. So let's write it back as a fraction, and we'll put 1 over 2x minus 1. Okay, we now have two logs where we're subtracting. Remember, we took out the negative, so the negative has become positive, the positive has become a negative. And we'll have the ln of 2x minus 1 minus the ln of 2x plus 1. And when you subtract logs, same base, they can come together and you do a division. So we'll end up with the ln of 2x minus 1 divided by 2x plus 1. And for the final part, we took the negative out, so now it's positive. And let's get rid of the negative exponent, and we'll get 1 over 2x plus 1. And we're still going from 1 to 2. Okay, we can substitute the values now. So let's put 2 in first. The negative a half stays out the front. Let's double bracket because we have to subtract the whole second value. And so we'll get 1 over 4 minus 1. That's 3, 1/3. Plus, well, we put 2 in. 2 times 2 minus 1 is 3, and 2 times 2 plus 1 is 5. And so we'll have ln of 3 on 5, and plus 1 on 5 when we substitute the 2. And then we're going to subtract, so open brackets. We're now putting 1 in, and so 2 times 1 minus 1 is just 1, and 2 times 1 plus 1 is 3, and so it's easier to find these numbers as well. So we'll have 1 plus the ln of 1 on 3 plus 1 on 3, and close our brackets. Okay, we can see that minus sign is going to get distributed to everything in the second brackets, and hopefully you would notice that you have a third minus a third, and so they're going to cancel out, and that's going to make our life a lot easier. So let's do negative a half, open brackets. We have ln 3 on 5 minus ln 1/3. And again, when you're subtracting logs, the base is the same, it can come together and you divide. So we'll have ln 3 on 5 divided by a third, which becomes 3 on 5 times 3. And for the last part, we have 1 on 5 minus 1. They're the only terms left. And 1 is 5 on 5. So 1 on 5 minus 5 on 5 is negative 4 on 5. And we have got something very simple now. Let's distribute the negative a half. So we get negative a half ln 9 on 5. And the 2 cancels with the 4, and the negatives cancel each other out, and we end up with plus 2 on 5. Okay, that looks like what we're trying to get to, but hopefully you would notice, oh, ours has got a 9 on 5, we need a 5 on 9, but we have a negative out the front. So we can take negative 1 from in front of the ln and bring it up as an exponent. And of course, rearranging, that will give us 2 on 5 plus a half ln 9 on 5 to the negative 1. And the negative 1, whenever you raise something to negative 1, numerator goes to the denominator, denominator goes to the numerator, so it flips around and becomes what we were looking for. The answer, 2 on 5 plus a half ln 5 on 9. Question 8 says, relative to the origin O, the points A, B, and D have position vectors given by, and we have 3 vectors for OA, OB, and OD. A fourth point C is such that ABCD is a parallelogram. Part A, find the position vector of C and verify that the parallelogram is not a rhombus. So whenever you have a question that's maybe a little bit hard to understand, a diagram is always helpful as it may shed some light and help us make some progress. So in this case, we definitely want to draw a parallelogram and then label the corners A, B, C, D, because that's what the question says. All right, the question also tells us that there's a point origin, O, and we know vectors OA, OB, and OD. All right, that point, that origin can be anywhere. It doesn't really matter where it is at this point. We're just trying to get a diagram to help us understand what's happening. All right, so in this situation, the first thing that we're asked to find is, well, what is OC? And what we do know with parallelogram is opposite sides are the same length and they're parallel, which is perfect because that's what vectors are. If you have the same vector, it's the same length and it's also parallel. So we can represent opposite sides of a parallelogram with a vector. Now to find OC on our diagram, we could do it in 2 ways. We could go, let's add OB to BC, and that will be OC. Or we could say, let's add OD to DC, and that also would be OC. Now DC, we don't know, but DC is the same vector as AB. So all we have to do to find OC is to add OD plus AB. And how do we find AB? Well, AB is OB minus OA. And right there, we've pretty much solved the first part of the question just by thinking. Okay, so we will have OC is equal to OD, which is 302, plus OB, which is 253, minus OA, which is 121. When we add or subtract vectors, we add or subtract the relevant positions. So for x, we'll have 3 plus 2 minus 1, which is 4. For y, we'll have 0 plus 5 minus 2, which is 3. And for z, we'll have 2 plus 3 minus 1, which is also 4. All right, so our vector OC is 4, 3, 4. We can write that using the unit vector notation. OC is 4 times I plus 3 times j plus 4 times k. For the second part of this question, we have to verify that the parallelogram is not a rhombus. Well, we already know it's a parallelogram. The question told us that, and we should know that because we made the opposite side the same vector. We made DC, the same vector as AB, and by doing that, we also made the other 2 lines parallel. Okay, so how do we show that it's not a rhombus? Well, we're going to use the difference between a parallelogram and a rhombus. There's 2 differences. A rhombus, all the sides are the same length, and in a rhombus, the diagonals meet at right angles. I think the sides are the same length for a rhombus is a good way. So all we have to do is demonstrate two adjacent sides are not the same length, and we'll use AB and AD. Why would we use AB and AD? You might be asking. Well, they gave us the vectors OA, OB, and OD, and A is between B and D. So it seems, given that they gave us those vectors, it seems like a good choice to make. Okay, so AB is going to equal B minus A or OB minus OA, whichever way you want to look at it. And AD is going to equal D minus A or OD minus OA. So we end up with AB is equal to 1, 3, 2, and AD is a vector 2, minus 2, 1. Now to find the length of these vectors, it's going to correspond to the length of the sides of the parallelogram. We get the length of AB is equal to the square root of 1 squared plus 3 squared plus 2 squared, and the length of AD is equal to the square root of 2 squared plus negative 2 squared plus 1 squared. So for AB, we get a length of root 14, and for AD, we get a length of root 9. Okay, well that's proven it for us. It's definitely not a rhombus because the adjacent sides are different lengths, and so it cannot be a rhombus. Part B is find the angle BAD, giving your answer in degrees. All right, well, this is actually very fortunate for us because BAD is the angle between the vectors AB and AD, and we were just using the vectors AB and AD, and we actually found the length of those vectors. So how do you find the angle between two vectors? Because if we find the angle between the vectors AB and AD, we will have the angle in the parallelogram, the angle BAD. So it's perfect. So all we have to do is find the angle between the two vectors. And the way that we do that is we use the dot product or the scalar product. And the AB dot AD is equal to the modulus of AB times the modulus of AD times cos of the angle between the vectors. Because we already calculated AB and AD in the previous part of this question, we can just do the dot product of 1, 3, 2, and 2, negative 2, 1. For the dot product, you multiply corresponding elements and add them together. So we'll end up with 1 times 2 plus 3 times negative 2 plus 2 times 1. And that gives us the dot product of minus 2. Okay, so we can rearrange the formula that we have and find out that the cos of theta is equal to the dot product or the scalar product, whatever you want to call it, divided by the length of AB times the length of AD, which we have already worked out as well. So cos of theta is equal to negative 2, which is the scalar product, divided by root 14 times root 9, and all we need is to work that out. So using your calculator, theta is going to approximately equal the inverse cos of negative 0.178. That is rounded, but we will use the exact value to get the angle theta is approximately equal to 100.3 degrees. Don't forget, if you're not told how to give your answer on the front of the exam paper, it does say when you're giving an angle in degrees as an answer, give your angle to 1 decimal place. Part C says find the area of the parallelogram correct to 3 significant figures. Okay, let's take that parallelogram again and have a little think about this. What we know is that we know the length of AB and we know the length of AD, and that's kind of handy because ABD makes a triangle, and we know how to find the area of a triangle given two sides and the angle between them. We have all of that information already. So we can find the area of this triangle by doing a half of AB sine theta. But the parallelogram is just two of these triangles together. And so to find the area of the parallelogram, we're just going to find the area of the triangle, multiply it by 2, and we have the area area of the parallelogram. Of course, the 2 is going to cancel out the half, and the area of the parallelogram is just length of a side times the length of an adjacent side times the sine of the angle between them. We know all of this information, so the area of the parallelogram is going to equal root 14 times root 9, which of course is 3. We've never said that. And we're going to multiply that by the sine of 100.3. But let's make sure we use the exact value, not 100.3. It should still be on our calculator for us to use. If we put that into the calculator, we'll get 11.0 something, but rounds down to 11.0. And that is our answer for the area of the parallelogram. Question 9a. The complex numbers u and w are such that u minus w equals 2i and u times w is 6. Find u and w, giving your answer in the form x plus iy, Cartesian form, where x and y are real and exact. Now you might be tempted to try and do some sort of substitution where you're putting in Cartesian forms for u and w. I think that would be a mistake. It's going to get complicated. You're introducing 2 unknowns for each of the variables there. That makes 4 unknowns and 2 equations very difficult to solve. Why can't we just work with u and w as they are? They're just the numbers, and we can just treat them as numbers. So let's do that and rearrange the first equation so we get u equals 2i plus w. Okay, then we can substitute that into the second equation. We will, of course, get 2i plus w in brackets multiplied by w is equal to 6. And we look at that and go, well, that's a quadratic. And the quadratic looks like w squared plus 2iw minus 6 equals 0. Okay, so we can't work out how to factorize by inspection, but we could use the quadratic formula. And you may be thinking, oh, isn't that going to be complicated? Well, inside the only complicated part is inside the square root. And if we were trying to do the square root of an I, it may be a little bit complicated, but inside the square root we get b squared. And once we square 2i, it's not complex anymore. So let's work with that. Of course, the quadratic formula, negative b plus or minus the square root of b squared minus 4ac over 2a. So in this case, w is going to equal negative 2i plus or minus the square root of, all right, when we take 2i and we square it, 2 squared is 4, and I squared is negative 1, so we'll have negative 4. And then we're going to subtract 4ac, 4 times 1 times 6, a negative 6. So you're subtracting a negative, which means we're adding, and we're going to add 24. And divided by 2a, a is just 1, so we're dividing by 2. Well, this looks really workable for us. That root 20 that we're going to have now can be broken up into root 4 and root 5, and we can, of course, solve root 4. So w is negative 2i plus or minus root 4, root 5 over 2. Root 4 is 2. We can divide the 2 into both terms on the top, and we'll get w is equal to negative I plus or minus root 5. And that's the answer. That's what they wanted us to give. All right, of course, and once we have w, we can find u because u is equal to 2i plus w. And so just add 2i to w, and you get 2i plus negative I plus or minus root 5. And so u is equal to I plus or minus root 5. If we put the associated solutions for w and u together, we will get w is negative I plus root 5, and u is I plus root 5, or w is negative I minus root 5, and u is I minus root 5. That probably would look better if we put the I second like they asked us to in the question. Well, we have a little bit of time, so for the sake of a comparison of methods, what if we did substitute with x plus yi, and what would happen and how would we solve it? All right, so we'd start off fairly similar because we can't substitute both of them. U is 2i plus w, do the substitution here, 2i plus w times w is 6, and make the quadratic w squared plus 2wi is equal to 6. We're going to leave the 6 over on that side this time. Now let's let w equal x plus yi, and we'll get x plus yi squared plus 2 times x plus yi times another I is equal to 6. Expanding the brackets gives us x squared plus 2xy, and then we have yi squared, so y squared, and when I is squared, you get -1, so it becomes -y squared. For the other brackets, we get 2 times x times I, which is on the right of the brackets there, and the other one will be 2 times y times I, or I squared. I squared is negative, of course, so it turns into -2y equals 6. Okay, so on the left we have a complex number in variables, and on the right we have, well, a number, but you could treat it as a complex number in numbers. And so we can associate the real part and the imaginary part together. So we need to collect the real parts together on the left, and we will get x squared minus y squared minus 2y is the real part. That's going to equal 6. And the other part is the imaginary part, which is 2xy plus 2x, put it in brackets, times I is equal to 6. All right, so what that tells us is the real part, x squared minus y squared minus 2y equals 6. And the imaginary part, 2xy plus 2x equals 0. Okay, you may be thinking, oh, this looks mightily complex. But when anything equals 0, and if you can factorize it out, it turns into something much easier to solve. So let's start with the second part first. Because it equals 0, we definitely want to factorize it. And we can take 2x out, and we'll get 2x times in brackets y plus 1 equals 0. All right, so the null factor law is our friend. That tells us that either x equals 0 or y equals -1. Now we need to test both of those situations. So when x is 0, we're going to put that into the other equation. And we're left with the y variables, but they're all negative. So let's move them over to the side where the 6 is to make everything positive. It will look a whole lot nicer. That turns into y squared plus 2y plus 6 equals 0. Okay, can we think of two numbers that multiply to 6 and add to 2? No, we can't. So let's try and solve for y then. And we'll get y, using the quadratic formula, is -2 plus or minus square root of b squared, which is 4, minus 4ac, 6 4s are 24, minus 24. We've run into a problem, and maybe we should have checked the discriminant first, but we get the square root of -20. And we can't do that. It's not a real number. Now remember, we were told in the question that x and y, the parts of the complex number, are real. And this is, y is one part, but this is not real. And so there is no solution here when x equals 0. All right, but don't worry, there's still the other variable. So when y equals -1, we're going to put -1 in for y, and we're left with the x squared, and then we get -1 squared will become just 1, so it's -1, and then we've got -2 times -1, which just turns into +2, and that equals 6. Okay, so this looks pretty easy to solve. Well, the -2 minus 1 is just 1, and we subtract that from 6, we get 5. So x squared is 5, and x is equal to plus or minus the square root of 5. So hopefully you can see that we've got to the same answer here. Remember, y is -1. Right, so for w, we're going to have the square root of 5 minus I, or w is -√5 minus I. And to find out u for each of those, we're just going to add the 2i, because u equals 2i plus w. And so u will equal √5 plus I, or u will equal -√5 plus I, and we've found the answers. Part B. On a sketch of an Argand diagram, shade the region whose points represent complex numbers z satisfying the inequalities. And we have the modulus, or the length of, well, let's go with the modulus. Z minus 2 minus 2i is less than 2. 0, so the argument of z is greater than or equal to 0, less than or equal to pi on 4, and the real part of z is less than 3. Okay, so to do this, first we need to make an Argand diagram. So we're going to have two axes, an imaginary and a real axis, and let's mark some values. All right, so for the first one, we're talking about a circle. and the numbers that are inside become the center of the circle. So in this case, the circle length is less than 2 or equal to 2, and so we're going to draw a solid line for the circle because it can equal 2, and the center of the circle is the z component that would make that 0, which of course is positive 2 plus 2i. And so it's 2 and positive 2 is the center, and the circle is going to have a radius of 2. Okay, so do your best effort at drawing the circle. Make sure you touch the axes at 2, 0 and 0, 2, and let's write the center of the circle as well. Okay, you can always put some numbers on the axes. That's always very helpful. Right, so the solution that we just found for the first inequality is what's inside of that circle. And that's the area that we got to keep in our mind as we keep progressing through all three of them. Right, the second one is saying the argument of z is between 0 and pi on 4. Well, pi on 4 is just 45 degrees, and 0 is effectively the x-axis, or the real axis of the complex number. Okay, so if we mark where that is, the real axis starts at 0, 0, goes out to the right, and if we mark out where pi on 4 is, you start at 0, 0 as well and go at 45 degrees up. Okay, so that means between those two lines is where the argument of z is greater than 0 and less than pi on 4. It can equal those lines as well because it's not just greater and less than, it's greater than, equal to, and less than, or equal to. So that's the region we're now talking about for the second inequality. All right, so remember that one, and let's go to the third one. The third one is where the real part of a complex number is less than or equal to 3. So on the real axis, we just go, where does it equal 3? Again, we're fortunate we don't have to draw any dash lines because in each case they've used it can also equal the value. So we're drawing a solid line where the real component part of the complex number is 3. Now, we're looking for anything that's less than that, so we're looking for the area to the left of that line and including the line. Okay, so if you can remember where those three areas were, we can shade the region on the diagram that we're told to shade, and that's all we have to do. Okay, so you can make it a little bit nicer, putting in some more information just in case they're looking for that when they do their marking. So the line at 45 degrees is the argument of z equals pi on 4, and the vertical line is the real of the complex number is equal to 3. And we're done. Question 10. We have a nice diagram of half of a sphere or a hemisphere. It's a tank containing water in the form of a hemisphere. The axis is vertical, the lowest point is A, and the radius is R, as shown in the diagram. The depth of the water at T is H. I have that in there as well. At time T equals 0, the tank is full, and the depth of the water is R. So, of course, it's the radius from the center to the bottom of A. At this instant, a tap at A is open. Water begins to flow out at a rate proportional to the root of H, which is the height of the water. And the tank becomes empty at time T equals 14. So when T equals 14, H will be 0. The volume of water in the tank is V. When the depth is H, it is given that, oh, that's really handy. V is a third of pi in brackets 3r h squared minus h cubed. It's good that we didn't have to work that out. Part A, show that h and t satisfy a differential equation of the form ht is equal to negative b is some constant divided by 2r h to the half minus h to the 3 on 2, where b is a positive constant. Okay, so we have two useful bits of information. One is a formula where the volume is a function of the height. Don't worry about the r being in there. R is a constant. it's not a variable. So the two variables are v and h, and that would give us a differential of v dv dh, which is not what we want, but that may be useful. The other thing they told us is that the flow out has a rate proportional to the square root of h. Okay, so we have a rate. And what is the flow going to be a rate of? Well, it's the amount of water, which is volume, compared to the time, because dv dt is a flow of water. All right, so what we can say then is that dv dt is proportional to the square root of h. And we know then that dv dt is equal to some constant k times the square root of h. Okay, so that's a good differential for us to have. Then let's go to the equation v equals pi r h squared minus a third pi h cubed and differentiate it, and we'll get dv dh is 2 pi rh minus pi h squared. Okay, that leaves us with, we can find dh dt now by using dv dt and multiply it by dh dv. The two dv's cancel and we're left with dh dt. All right, so let's multiply them together. We'll get k times the square root of h multiplied by 1 over 2 pi rh minus pi h squared, because we had to invert it, we had to flip it upside down to get dh dv. All right, if we put those together, and let's try and make it look more like what we're aiming for. So let's factorize the pi out from the denominator, and we'll get k root h on the numerator and pi, and in brackets, so it looks kind of similar to what we're aiming for, 2rh minus h squared. Okay, b is a constant on the top, and so we need to get rid of the h. How can we get rid of that? We can multiply by 1 over root h on the numerator and the denominator. That would get rid of it, which of course is just the same thing as multiplying by h to the minus a half. That's 1 over the square root of h. Okay, and if we do that, and let's take the pi up to the top, because there is no pi on the bottom in our answer. So we'll get k on pi divided by h to the negative a half times h to the 1 is just h to the half. So 2r h to the half minus, and h to the half times h to the 2 is h to the 1.5 or h to the 3 on 2, which is great because that's what we wanted. And we're pretty much there. To make it look like what we're aiming for, that b on the numerator is going to have to equal negative k on pi. So if we go to what they gave us, and instead of b we put negative k over pi, we would have what we were able to get to as the solution. Okay, but you may be thinking, but didn't they say that b is a positive constant, and it says here negative k on pi? What that simply means is k has to be negative. If k is negative, then you have negative, negative, which makes it a positive, and b is positive. So let's write that down just to show the markers that we know what we're doing. And we will get to dh dt is equal to negative b over 2r h to the half minus h to the 3 on 2. Part B says solve the differential equation and obtain an expression for t in terms of h and r. Okay, if you weren't able to get the first part, hopefully you'd be able to make progress in the second part by taking what they gave and get some of those 8 marks there. So let's start with the differential and work from there. dh dt is equal to negative b over 2r h to the half minus h to the 3 on 2. We need to move all the h variables to the left and any variable that's not a h on the right. Well, there are no other variables. Everything else is a constant. All right, so if we take up the denominator, and let's take the minus sign with us instead of leaving the minus sign behind. That's going to make the 2r h to the half negative, and it's going to make the h on 3 on 2 positive. All right, so let's put that first. We're going to put h 3 on 2 minus 2r h to the half dh, And on the other side, we're left with b now, because we took the negative over, and we're going to move the dt onto this side as well. Put integral signs at the front, and we're good to go. We can integrate those now. H to the 3 on 2 would have come from h to the 5 on 2. We need to get rid of the 5 on 2, so we put 2 on 5 out the front to cancel it when it comes down. 2r just stays there as a constant. H to the half would go to h to the 3 on 2. We need to cancel that, so we put 2 on 3 out the front. And that is equal to, b just integrates to bt, and don't forget to add your constant c. All right, we need to find out what these constants are. And we know 2 bits of information. At time equals 0, we actually know the height of the water is going to be r. Now remember, r is not a variable, it is a constant, it's a value. So when t equals 0, h equals r. The other thing we know is that it was empty at time equals 14. So when t equals 14, we know the height again, and this time the height is going to be 0 because there's no water in the tank. Now we can use that information to hopefully find some of these variables. Let's start t equals 0. That's always nice when your time is 0, because anything with a t just disappears. So t equals 0 and h equals r. Okay, so for the first part, we're going to get 2 on 5, but instead of h, we're now going to write r to the 5 on 2. And then we're going to subtract, all right, the 2/3 times 2 becomes 4/3. And we're going to have r times r to the 3 on 2, which is r to the 2 on 2 plus 3 on 2 becomes 5 on 2 as well. And on the other side, the bt disappears because t is 0, and we're just left with c. So now we have what c equals. Those are the same, so we can put them together, and we get 2/5 minus 4 on 3 becomes 6 on 15 minus 20 on 15, which is negative 14 on 15 r to the 5 on 2 for c. Okay. Now, when we can use the other substitution, when t equals 14, h equals 0, and we're going to replace the c at the same time. All right, this one actually is much nicer, because when h is 0, a lot of things disappear. On the left, the first term disappears because 0 to the 5 on 2 is just 0, and 0 times anything is 0. And the next term disappears as well because it just all becomes 0. And we're left with t is 14, so we have 14b, and we've got plus c, but c, you may remember from the previous slide, is negative 14 on 15 r to the 5 on 2. So if we take that over, it will become positive 14 on 15 r to the 5 on 2. And we divide by 14, it's going to cancel and just leave us with b is equal to 1 on 15 r to the 5 on 2. So we can put the equation together now without the b and the c. And we will have 2/5 of h to the 5 on 2 minus 4/3 r to the h to the 3 on 2 is equal to 1 on 15 r to the 5 on 2 t minus 14 on 15 r to the 5 on 2. Now we were asked to find an equation where t equals something, so we're going to just not worry about how complex it looks, move everything away from the t and see what happens. The first thing we move away is the minus 14 on 15 r to the 5 on 2. Take it over to the other side and we're going to add it. So let's put t on the left to make this look a little nicer. And we'll have 1 on 15 r, 5 on 2 t is equal to 2 on 5 h, 5 on 2 minus 4 on 3 r h, 3 on 2 plus the 14 on 15 r to the 5 on 2. Okay, so we're multiplying t by r to the 5 on 2, and we're dividing it by 15. So when we take those over, we're going to multiply every term by 15, which is nice. It's going to get rid of those fractions. And we're going to divide everything by r to the 5 on 2. And so we get 2/5 times 15 is 6, h to the 5 on 2, minus 4/3 times 15 is 20. So we've got 20 r h to the 3 on 2, and 14 on 15 times 15 is just 14. So plus 14 r to the 5 on 2, all divided by r to the 5 on 2. Right. It may look nicer if it's not a big fraction like that. So let's take the r into each term. It can, of course, go to the top by making it negative, and we would have 6 to the r to the negative 5 on 2 times h to the 5 on 2. minus 20. We've got r to the 1 minus 5 on 2, which is 2 on 2 minus 5 on 2, which is negative 3 on 2. And h to the positive 3 on 2 plus r to the 5 on 2 divided by r to the 5 on 2 is 1. And so we're just left with 14. Well, that is an adequate answer. So you could leave it like that and you should get full marks. But if you pay just a little bit of attention there, you'd go, those, in each of the terms, the powers are the same amount, like the 5 on 2. So we could collect those and just have one power, and it would become t is equal to 6 in brackets, h on r to the 5 on 2, minus 20 in brackets, h on r to the 3 on 2, plus 14. Maybe it looks a little nicer, but it is the same equation, and both of those should be correct.